Hi everyone, and welcome back to Design Week 2023, here live in Chandler, Arizona. I'm your host, Ulysses, and this is day 3. On the first day, we covered embedded design tips and tricks. On the second day, we covered securing the cloud. And today, we will cover technology in the wild, demos to help you along your journey and inspire you. But before we get started, I'm going to pass it to Nate in the booth, who will let you guys know how you can participate today.
Hello, and good morning. I'm Nathaniel Thompson, and welcome to Day 3 of Design Week Tech in the Wild. We are streaming from YouTube, Facebook, and LinkedIn. So if you like what you see, please like, comment, and subscribe. Now, if you have any questions, feel free to leave them in chat, and we'll get to them at the end. If we can't get to your question, or if you have any more, feel free to email us at livestream@microchip.com. And before I pass things back off to Ulysses, I want to tell you about our Design Week webpage on microchip.com, where if you go there and hit register, it'll take you to On24, where you can view more Design Week content from our experts all around the world. Back to you, Ulysses.
All right, thank you, Nate. Now, before we get started, I'm going to introduce my guests. So we have Bob, Ross, and Josh. So to my left, we have Josh. Hi, Josh.
Hello, Ulysses.
In the middle, we have Bob.
Hi, Bob. Ulysses. Happy to be here.
And at the very end, we have Ross. Hi, Ross.
Good morning, Ulysses.
All right, so we have 3 demos that we're going to go over today. So let's get started with the first one. Bob, could you give us an overview of what the Sensor Cube demo is?
Certainly. In playing on the theme of technology in the wild, we have 2 flavors of what I call this Sensor Cube platform, both based on, well, as you can tell, they're cubes. This is MakerBeam, which I love using for the 3-dimensional aspects of demo builds. The first demo here, which I call Sensor Cube Type 1, is a demo more used for outside environmental monitoring. It's based on the AVR mini cell board. I have a local OLED screen just because I like to have local feedback with or without a UART connection. And on the back, I'm employing 3 sensors. The top 2 are from Sensirion. The first one is an SCD40, which is a true CO2 sensor, and I'm going to get to that in a minute and why that's important. The middle one is a VOC sensor, and the bottom one is a sensor I use quite a bit when I'm doing atmospheric monitoring or demos of this, is a Bosch BME 280. I've been using it for years, and it's just literally just a plug and play. What I want to emphasize in this demo, or in this demo system, and as the other sensor cube I'll get to in a minute, is the rapid prototyping aspects of it. Not only the framing of the MakerBeam, but the fact that all these sensors here and our AVR Mini Cellular IoT board are all completely supported in Arduino. So all the code development I've done on this system is in Arduino. And that allows me to, combined with, you'll see this, it's hard to see here on contrast, but much, much cleaner on this side, is the daisy chain, which is an I2C, which is called Stemma or Quick, an unofficial standard created by Adafruit and SparkFun, which is just, again, a daisy-chained I2C bus where I can literally plug and play different sensor pads because both companies produce boards with this connector on it. So this allows me to optimize the combination of sensors that produce that global aggregate of data that I'm looking for. The other aspect of the rapid prototyping is I wanted to make sure that, or I wanted to reduce the burden of the decisions needed to be made on what type of cloud structure or dashboard. I simply wanted a very easy way to validate that I'm pushing MQTT data up to the cloud. And if Ross can bring up that dashboard, I came across a lovely
oh, sorry, it's on the other thing. My apologies. There we go.
Okay. No worries. This is a company called HiveMQ. They play nice with Azure or AWS. They're agnostic. But what drew me to them is that they have this WebSocket interface which provided me with a zero-code solution to validating my MQ2 data being pushed up. So unlike having to spend some time on my dashboard creation, my dashboard design, I'm still at the hardware, software, edge node optimization level, and I wanted to stay there. So I wanted very quick, again, validation, and HiveMQ provided that. So that's sensor cube number one. Again, more for outside. Moving on to sensor cube number two. This, again, is based on a AVR Curiosity Nano. This is the AVR 64DD Curiosity Nano. Also supported by the Arduino IDE. All the code running on this cube is also Arduino. And on the back, it's a compound sensor. This sensor is, again, from Sensirion. I'm a big fan of their sensors, by the way. This is a particulate matter sensor, the type of sensor you would find in a humidifier or in HVAC systems for air quality. It measures PM 1 micron, 2.5, 4, and 10, along with noxious gases and relative humidity and temperature. So at this time, right now, I didn't pick up an RF channel, and I am upgrading this cube to now use Bluetooth. This one is battery powered, this one is not, because this particulate matter sensor actually has a fan in it. So it's not, it could be low power if I power gate it, but the point is this sensor's more for indoor, where you're probably gonna likely have a power supply from the wall. So I wanted to cover one more thing on, which is I have a background in environmental monitoring. And I wanted to point out that it's important, there are families of sensors out there relating to this true CO2 sensors. There are families of sensors out there that use synthetic numbers to calculate CO2. Please make sure, if you're looking for a sensor system, please make sure that it's a true CO2 sensor. Okay, they're a bit more money, but the accuracy is far worth the cost. And you will also, VOCs, for those of you volatile organic compounds, typically, and this isn't global, if it smells, it's a volatile organic compound. Body spray is a volatile organic compound, so is the rubbing alcohol in the hand sanitizers. These tend to give you various indexes depending on the manufacturer, which is usually enough. As you go up in price on these sensors, they will actually disseminate between the actual type of environment or gas or compound that you're sensing. So with that, these are the current cubes as set, and we're moving forward with these designs. So.
All right, since we have so many sensors, how many microcontrollers does each one have?
There is only one microcontroller in controlling both the display and the sensor readings. So that the I2C bus is a very popular bus in modern sensors. And the reason for that is it allows sensor companies to integrate their complex analog front ends with a very robust and inexpensive, I avoid using the word cheap, inexpensive interface of I2C, which allows you to string sensors very effectively. The time constant or response time of these sensors is slow enough that, I mean, I2C isn't that slow, relatively speaking, but it allows you, most new sensors now are I2C.
Yeah, and after installing all those sensors, how much memory do you have left?
That's the nice part. Again, the protocol is fairly simple. The heavy lifting for the LT modem on here is done by the Sequans modem. The whole software flash load on this sensor cube is around 33 kilobytes, which leaves me around 90 kilobytes of space. So the AVR DB 128 DB 64, or sorry, 48 on this, you have tons of room. You're probably going to run out of your app's going to be horrendously, that's 128K is a big 8-bit application. This one is running slightly north of 17K right now. And that's on a 64K flash. Again, the RAM footprint is very tiny. So there's plenty of overhead to move forward with both these platforms.
All right, and since you started, do you have any future plans for this demo?
There are some future plans for both. I need to make this LTE one a lot more fault tolerant, but then there's a return on investment for a reference design, how exactly fault tolerant I want to make it. I could make it completely fault tolerant, so I could just leave this in a bush and someone would probably rip it off, but as long as the battery lasted and I threw some solar panels on it. So there's some fault tolerance, especially in the LTE. I'm looking at different sensor combinations. Another interesting thing is when you have multiple sensors, all these sensors have temperature readings. What is the truth? Who's the right temperature? Temperature is a very basic construct, or a very concept that people understand, but I can guarantee you I'm only publishing one temperature, I believe off the BME 280. I guarantee you all three sensors are reading a different temperature because of different self-heating. So there's all these little subtle things that you need to think about. But people go, oh, I got 3 temperature sensors, they all should read the same. Yeah, no, never, right? So yeah, and just general optimization. I'm adding an RF channel to this. I'm adding Bluetooth to this sensor cube. So that will allow me to set up multiple stations within a building and then walk around and just log from the phone. So.
All right. Thank you very much.
All right.
Is there any place people could go to learn more about this?
Yes. So the primary information about the LTE, the AVR Mini Cell Board, is at iot.microchip.com. Both of these cubes will be published on our GitHub, and as well, I'm creating articles for both of these going to be published on hackster.io.
All right. Thank you so much.
Thank you.
And now let's move on to our second demo of the day, the cold plate. So Josh, would you mind showing us the cold plate and giving us an overview of it?
Sure. So this is the cold plate. This is a demo me and my fellow application engineer, Robert Perkel, have created. It is used, I'm going to turn it on real fast to let it cool down. So as you may have guessed from the name, it gets cold on this top surface, and that can be used to chill a beverage like a cup or used for scientific applications if you need anything chilled. It's basically the opposite of a hot plate. This demonstration is not for purpose or meant to be recreated in its entirety, and it's not what we're doing that I want to focus on, but how we're doing it. On the side, you'll see the control board that drives everything you see here, but it's only driven using a single 8-bit microcontroller as the brains of the operation. There aren't a ton of discrete components. Instead, we are able to utilize the built-in core-independent peripherals on the microcontroller for all of the functionality. We are hoping that you see this project, see something you like, and are able to take that portion and copy and paste it into your own design using our core-independent peripherals and the unique ways we chain them together. So instead of just throwing more processing at an application, we're using the right tool for the job and doing it very efficiently. So since you can't be here to feel it cooling down like I can, we've painted the top and this cup with thermochromic paint that is yellow, and then when it gets cool to 10 or 15 degrees Celsius, which is, I think, at like 50 Fahrenheit, it will turn red. So you can already see the logo turning a little red, and then hopefully as we talk, you'll be able to see it propagate up through the cup as things get very chill.
So you mentioned that some aspects are controlled by core-independent peripherals. So what parts of that are controlled by them and what instead of code? Yeah,
so first we have tri-temperature monitoring. So the plate temperature, the heat sink temperature here in the center, and then the board temperature. So the board temperature is monitored through a proxy. The microcontroller reports its own temperature. So as the board gets hot, the microcontroller temperature will increase. So we're monitoring all three of those using the single analog to digital converter that's internal to the microcontroller, so we don't have to get a separate discrete part. And there's an internal analog mux that's doing that for us. That way we can intelligently modulate the temperature instead of just turning it on and keeping it on. There is a central cooling fan in the heatsink here that we are controlling with the micro using PWM and monitoring its tachometer signal using a timer in a creative way. And since we're monitoring the heatsink temperature, we can spool that fan, and so it's not just always on. We can have a sloped ramp rate, and DC fan control using a microcontroller is a great application for it. There's current monitoring and measurement, so on the user interface on the front, we can see how much current is being pooled, as well as we have a threshold detection. If there's a short circuit or a wire becomes unplugged, the microcontroller immediately responds. There's an app note on our website implementing a Peltier controlled cooler using an 8-bit microcontroller. It talks a little bit more about how we do that, but it does it in a unique way that we don't have to wait for an ADC acquisition like we do for displaying the current being pulled on the UI, so we get that immediate response. There's also functional safety supported setting storage, so the setting you write is validated with a CRC, so that if you're using it for scientific application, no settings get changed when you turn it off and turn it back on, so you know that what you store is what you get. Then there's protective system monitoring using a watchdog timer in case there is a bug in the code, which I hope not. I don't want to write bugs. The system can reboot and attend to the safety critical tasks, such as making sure there's not a short circuit or something's not getting too hot or too cold. The important things can get monitored. Then lastly, there is the user interface that's all controlled using CIPs. There's a I2C driver on the microcontroller that's running the display, where we've hooked up some CLCs in a creative way to monitor a rotary encoder instead of just having to constantly pull it, as well as monitoring the push button for navigating the menu.
Since this is just a demo, what parts of it can be used in other applications?
And I think hopefully all the parts, but in particular, some great. My favorite part is the thresholding system, what tells versus the short and open system, the short versus open wire, if there is a short. That's needed in pretty much any electrical application, and once again, it's all internal to the microcontroller. It's using a DAC, some comparators, and a CLC, which isn't too complex. There's also that fan speed and control monitoring for the central cooling fan. Fan control, very prevalent application for instead of having to get an IC, using that on a microcontroller that you might already need. Very useful, as well as decoding a quadrature encoded signal without having to spend a ton of processing on it. So if you want to use that for a volume knob or even monitoring low-speed motors, that's another great application.
So speaking about the microcontroller, why did you choose this particular MCU?
Okay, so for the microcontroller for this project, we're using the PIC16 F17146 microcontroller on the side, right there. The main reason we chose this is its impressive analog portfolio. We knew we needed that ADC for measuring the different temperatures, as well as for that threshold comparison system. Those were two of the design requirements we really wanted. And not a lot of microcontrollers have that built-in analog. Because we have such a wide array of analog CIPs for that threshold system, we knew the 171 was a great choice. It also has all the timers and serial protocols we needed for the display, and then we could have some debugging, as well as the multiple timers like the heartbeat timer for the watchdog, and various other ones like counting the PWM, the tachometer signal from the fan. And it has the MSSP for the I2C, as well as the CLCs we needed, and built-in op-amp, all internal to the microcontroller, which gave us a lot of flexibility when designing the system.
Yeah, and as you were making the demo, what challenges did you face?
A lot. So probably the one that I faced the most was designing the power circuit. That's not my area of expertise, but thankfully Robert Perkel was able to figure it out. Smart guy. So hi, Robert. Shout out to you. But then also the hardware, building the actual physical enclosure was kind of a challenge. But once we got into the coding side of things and developing the actual software, the development process speeded up rapidly, since Robert and I were both able to use our toolchain MPLabX, as well as the microchip code configurator. So all of these core-independent peripherals, we didn't have to read through the data sheet and go ahead and set all the bits. We could use the graphical tool to quickly modify and change things as we're going through that rapid development phase, which got us up to speed very quickly. And then it made debugging way easier too, since we could change things on the fly and then incorporate our code and then get it all working together.
All right, awesome. And where can people go to learn more?
So I mentioned earlier there is an app note on Microchip's website. It's app note AN4889. if you have a good memory. Then there's also a GitHub repo on discover.microchip.com if you want to read more about it, as well as a Hackster post.
All right, very cool. And that brings us to the end of their second demo. And let's go on to our third demo. So Ross, could you give us an overview of the Agri IoT demo that you have?
Sure. So the first thing I want to do, can we cut to my monitor here? Because I want to show the dashboard here. So we're monitoring the temperature, the humidity, the atmospheric pressure or barometric pressure, as well as the soil moisture. And we can see the soil moisture just here reading 49%. Now this is taking a sample every 3 minutes. So I'm going to give the plant water and then we're going to come back to this. All right, so that's a bit of a water. So now let's actually dive into this. So if we cut to the camera here that's above me, we are using a Curiosity Nano development platform with the AVR DD Curiosity Nano. We're using the Bosch BME 280, which is the same sensor that Bob was using just before, and that's on the weather click that's made by Microelectronica. And then we're using one of our LoRa modules, which is the RN2903, and that's the LR2 click. And so what we're doing is we have a capacitive soil moisture sensor in the plant here, and we're taking analog readings of that, as well as those atmospheric readings that I was just talking about. We've also been working on developing a circuit board from this, so we've integrated the capacitive soil moisture sensor here. We have the microcontroller on board, we have power control, we have battery holder on the back, and of course the RN2903 module here. So it's an all-in-one device, and we're working to release that on GitHub later on. For people who want to find out more, first of all, we have an article that one of our engineers, Grace, wrote about 8 bits and smart farm technology, both for agricultural and livestock. We have the Microchip University, or MU course, and that is hosted by Bob Martin here. And all of these links are going to be in the chat for you. We also have a Hackster.io article. So this project was born out of a capstone project, and we identified one member of that capstone project, it's Toby Sinkinson, and we hired him as an intern, and he's now one of our full-time engineers. And so he's continued to work on this project with us, and he's written this full Hackster article, which enables you to get up and running, and it also links to the GitHub repo, so you can actually build this yourself.
So what sort of challenges did you face throughout this project?
Oh, we faced quite a few challenges. First of all, because we're based in Phoenix and the summer temperatures here are 45 degrees Celsius, which is about 115 Fahrenheit, it means that a lithium polymer battery, it can't be used because we're well beyond its thermal limits. So that means we had to look at different battery chemistries. We eventually settled on the lithium thionyl chloride battery that gave us the output that we needed, as well as not turning into a spicy pillow, if you will, during the heat of the summer. We also had some issues with salinity. So we found that when driving the capacitive soil moisture sensor with PWM, if there was a certain amount of salt in the soil, it could skew those readings. And so we've been working to increase the PWM frequency of that capacitive soil moisture sensor. But there's also a limit to what you can do there, because as you increase the frequency that this is being driven by a PWM square wave, you then start to enter RF territory, and that can interfere with the radio that we're working with here. So we have to find the sweet spot that gives us some resistance to the salinity skewing the readings without affecting the radio. We also had some issues. Well, we were looking at weatherproofing this, because obviously if it's going to be out in the field, we need to find some way of preventing water ingress in the form of rain, or whether it's flood irrigation, which is quite common here in Phoenix. There are also terrain issues. So when we were testing this in the back field, behind Microchip here, there is actually a large dirt berm. And so we had to make sure that we had a good line of sight between our device, which is down near the ground, and that itself causes a whole bunch of problems with attenuating the signal. So you need to get the antenna sufficiently high enough away from the ground to limit that attenuation. At the same time, you also have to put your gateway up sufficiently high so that you've got a reasonable line of sight, and so you can get your data flowing rather than losing packets.
If someone's interested in this demo, can you buy this demo or parts of it?
You can buy all of these parts of this demo here. So the 2 clickboards are available from Microelectronica. So it's the weather click in the LR2 click. We have the Curiosity Nano, so that's the AVR 64DD32 Curiosity Nano, and it has the onboard programmer debugger. It has all of your pins broken out. It has a user button and a user LED, and of course the baseboard, which ties the whole thing together and enables you to easily work with this as the development platform.
All right, awesome. Where can people go to learn more?
So you can go to the Hackster article that Toby has written, and you can also go, and we have a YouTube video that Toby made about this, and you can actually see us in the backfield testing this. And then the last thing is, of course, is the GitHub repo, and that is also linked through the Hackster article.
All right, could you show us if the soil has changed?
Let's do that. So let's take a look. My soil moisture. So we're seeing here, it's showing 100%. The graph hasn't yet updated. The graph updates with less granularity than the graph. Sorry, the graph updates with less granularity than the actual reading, but we can see the soil moisture is showing 100% now that I gave it a good water.
All right, thank you so much.
Cool, thank you.
Do we have any questions from the audience?
Yes, we do. Give me 1 second. I've been collecting and grouping them all up so I can ask person by person. So let's start with Bob Martin. So first and foremost, we have a question from a user asking, was the Arduino code imported into MPLab?
The Arduino code will be imported into MPLab X. I am just finishing the beta test for a plugin for MPLab X to validate, to pull in the actual Arduino code, and this is a big step. For those of you who remember, years ago I used to teach a course on importing through Microchip Studio. We've extended that into the newer cores in the AVR family. And yes, this is going to be an important step moving forward as I show people how to progress from the more complex things you can do with the new AVR families, the bigger memory footprints, the improved peripherals, the power of the peripherals. And I'm working with capstone teams to further improve that performance of the peripherals and what's called a core support thing called DX Core, written by an outstandingly brilliant young man called Spence Condi out in the East Coast. So we're just on the threshold, and I will be teaching classes for the in coming up and toward the end of the end of the year on importing sketches and showing how you can do source level debugging of Arduino sketches along with optimizing that code, having that breakpoint data, direct data inspection. So serial print line for debugging is going to be your last resort.
Okay, and another one. What RAM and flash memory storings in sorry, I have to read this one real quick. So what's your memory usage on these sensor cubes?
As again, the LTE based one, Sensor Cube 1, the flash footprint is a little north. I think it's about 33 kilobytes, and with about a kilobyte-ish of RAM. The second one, much smaller footprint, it's a little north, it's about 17 or 18K. And I think literally just under a kilobyte of RAM. I'm not really worried about getting full optimization for the code itself right now, because I've got plenty of space in both aspects of RAM and flash. As I move towards more fault tolerant, especially on the LTE-based one, because it's going to be, I would like to get these set out in the field and in friends' houses or whatever, just to do some long-term testing. I'm well under. I have plenty of space on both parts, so I'm very happy with how those projects are pulling together.
Okay, and then two more for Bob before I move on to Josh. So are there more sensor cubes being considered, and is there a limit to a number of sensors you can connect?
There are more sensor cubes being considered. Sensor Cube 3, I previously mentioned during the program that that they're again, well, there's Sensor Cube 3 is going to be looking at various different variations of the VOC and the CO2 more so, but it's going to be more plug and play. I'm going to be adding more automatic support going forward where the code will actually recognize the type of sensor I've injected and implement the correct driver code. And that's the beauty of the rapid prototyping in the Arduino environment is Sensorion and again Bosch through both Adafruit, SparkFun, and Sensorion itself is actually providing direct Arduino library support for all their new sensors. So Sensor Cube number 3 is going to be more about doing comparisons, not so much to show the faults but to allow me to more easily find optimum temperature offsets. That's where I was going. Sensor Cube 4 is still under consideration, but probably going to be adding some more structural changes in the circuit boards. I'm cutting small circuit boards for these as well. The Gerbers for all of these will be published on the GitHub. That will allow me for more intrusive power optimization monitoring. I want to look at, get in and measure current off the sensor deck versus the microcontroller and be able to pull out all those current measurement points easily without butchering the board.
Okay, thank you. And then actually one more for Bob. How are you going to approach the power management schemes?
Power management, again, hopefully Sensor Cube 4 is going to help me move along, but obviously there's some low-hanging fruit on Sensor Cube number 1 because every one of these sensors, practically has a green LED glowing, so that's some obvious low-hanging fruit. I do have on the purple, it's hard to see because of the contrast, but I've cut a small purple PCB adapter board. I do have a current measurement monitor shunt installed, and it's sitting down and finding the right balance between especially these types of sensors have a finite warm-up time. It takes a while, especially for things like the VOC sensor, to actually give you good data. So if I power gate everybody, it takes a while for all the sensors to get to readings that make sense. And I have to balance that with, do I keep the sensors on? Do I keep some sensors on? So do I power gate every sensor individually or as a bulk group? And then deciding what's the most optimum frame format because once I turn on the Sequans modem, for the LTE modem, I am now using a lot more power. So obviously you want to make your data packets, your MQTT packets, as efficient as possible because transmission is power. And power is, from my little LiPo battery back here. So that's, it's a very iterative process. So that's, the first step is low-hanging fruit.
All right, thank you very much, Bob. Moving on to questions for Josh. So first and foremost, how does the cooling element work?
So the cooling element on the cold plate is a Peltier element, which acts as a solid-state heat pump when current is flowing through it. So the element's actually installed right underneath this plate here, and above the heatsink, it's pumping heat from the plate into the heatsink because it's changing the. As long as there's a set temperature delta based on the amount of power, so as long as we're able to cool this heatsink, we can keep getting the plate cooler and cooler.
Okay, thank you very much. Next question for Josh. How much memory does the cold plate use?
That's a great question. It uses about 70% of the memory on the PIC16 F171, which is 11K out of its 16K flash. So we still have a fair amount of room if we want to add more features, and that's thanks to the fact that almost all the functionality is built into core-independent peripherals, which are just registers instead of tons and tons of code.
Next question for Josh. Where is the control board from?
Where is it from? So this is a custom control board that Robert has spun. If you want to recreate it, all the BOM, schematics, and code is hosted on the GitHub repo or on discover.microchip.com Ulysses showed earlier. And then if you want to recreate the board or see how we did certain things, check that out.
All right, wonderful. And another one. So if the board overheats or something goes wrong with if there's like a thermal runaway on the thermal plate, what will the board do? How will the PIC16 handle that?
If there's a thermal runaway, well, it will respond differently depending on where the thermal runaway is. If it's on the board, like you said, the microcontroller temperature, once it crosses our threshold for unsafe operation, it will easily be able to shut off the Peltier element and cut the power that is being cooled that is causing it to overheat. If it is in, it will respond similarly for the heatsink, and then reverse for the cold portion up top. If it gets below the temperature set plus there's a hysteresis setting, then it will also shut the power down, and we know that's going to happen reliably because of the Windows watchdog timer.
All right, cool. And then last question for Josh. So aside from the Peltier plate, and also kind of going back to the what we were talking about with thermals, what other sensors are being used in the cold plate? And can you talk a little bit more about the details about like how it monitors that?
The sensors other than, so the sensors that this has is there are two thermistors and then that internal temperature sensor on the microcontroller. The thermistors are monitored using an op-amp and ADC setup. The op-amp amplifies the incoming resistance or voltage that is being measured by the voltage divider to amplify it so the ADC can get a better reading. Actually, the op-amps we have can use a dynamic resistor ladder, so as the value that is coming in is fluctuating, we aren't stuck with a static resistor ladder, so we can change the gain on the fly if we needed to. In terms of other sensors, I guess you would call the tachometer input. That's coming, the tachometer output from the fan that's coming as an input to the microcontroller. That's a sensor, so we're able to, since we're just applying a PWM signal to the fan, we don't know its actual RPM. So this tachometer signal that's coming in is fed into a timer, and then the microcontroller can just periodically check the timer, know how many pulses have occurred since it last checked it, and derive the fan's RPM.
Awesome, thank you. So moving on to questions for Ross. So first and foremost, how does a grower differentiate between node data?
Oh, that's a good question. So, because we're only showing one sensor node here, but you would have a farm that would have multiple sensors along a row and many rows. So you can actually dedicate specific ports to sections of a farm. So for example, you could have row 1 being ports 10 to 19, row 2 being ports 20 to 29, and so on and so forth.
All right, awesome. And another question for Ross. Can this project be adapted for different sensors or different applications?
Absolutely, because if you're developing it on the Curiosity Nano platform, you can simply change out whatever sensors you're using. So if you didn't want to use the Bosch BME 280, you could use a different sensor. Of course, you would have to adapt your code and pull in the libraries for that to work with it. And if you wanted to use a different radio, you could do that as well.
All right, thank you very much. Give me a second to scroll. There was one more question for Ross. Oh, found it. So currently, how many days does the battery support for the Agri IoT with LoRa?
Currently, with the testing that we're done, we're aiming for at least 6 months. We haven't done long-term battery testing yet, but we want to do some field testing coming up soon, and we'll be able to answer that more accurately later.
Okay, and I found another one for Ross. So how many feet, so when you check the soil moisture, how many feet down can it go? And what are there any fail-safes if a temperature sensor fails?
So in terms of depth, we are currently limited to the length of this capacitive soil moisture sensor, because if you buried the whole thing in the ground, obviously the radio will not be able to transmit. And the second part, sorry, what was the second part of the question?
We have a user wondering if there's any fail-safes if temperature
If the temperature
fails.
sensor fails. We currently don't have a backup for that, but we are working on a different version that will also have soil moisture sensor, so you would at least have some degree of understanding of what's going on with your soil moisture. But we don't have a second temperature sensor there.
All right, thank you very much. So I actually had another question come in for Bob. The sensor cubes, what voltages are they running at?
Currently, this sensor cube is being powered by a single, what's called a 1S 3.7. The base voltages here are 3.3. We have an onboard voltage regulator on the AVR mini cellular board, and coincidentally a very nice battery management system. So you can punch in 5 volts and it will, the battery management IC will both not only properly power the AVR IoT mini cell board, but charge the LiPo battery. So sensor cube number 1 is essentially a 3.3 volt system. There are aspects of, and this is another interesting thing, the AVR DB, along with its smaller brother, the DD, supports multi-voltage I/O on its I/O rings, which essentially we needed that, and it allowed for very efficient implementation of the AVR mini cell board, because the Sequans modem, its signaling interface runs at 1.8 volts. And that allows us to directly interface to the Sequans modem without having to put external voltage translators on board. It's all taken care of by the AVR DB. Similarly, the sensor cube number 2, the interesting thing is we have 2 voltage planes here. The bulk of the system is at 3.3. The AVR DD 48 is running at 3.3, so is the OLED display. However, the interesting thing is with this SCN55, and that's another reason I didn't go for a battery-powered system, or if I did, I would have to go probably to a 2S or a 2 times 4.2, like the 8-ish volt 2-cell lithium polymer, is because the power supply for this Sensirion SCN55 is 5 volts. However, its signaling level is 3.3. So the primary voltage domains on this one are 5 and 3.3. I'm looking at step-up voltage converters to go from a standard, 3.7 to 4.2 is what you get out of a standard 1S LiPo battery to power this guy. But again, these are some power optimization trade-offs that I will be looking forward as I move the cubes forward in optimization for power and efficiency. So yeah, so here we have essentially 5 volts coming in if I'm coming in looking at the serial stream coming out of it, but primarily right now it's operating at 3.7 to 4.2 coming in, voltage regularly down to 3.3, which is the majority of the voltage planes powering the board, or the AVR DB, and the sensors themselves. Those are all running at 3.3, although they can handle 5, and then the hidden voltage plane of 1.8 running on the Sequans modem.
All right, and then I have one final question, and this one can pretty much go to everyone here. But what software do we use to develop these demos?
Well,
I can take that one.
Yeah.
Okay, all right.
So we're using our MPLab X IDE. We're using our XC8 compiler, and we're also using the microchip code configurator, or MCC Melody, to set up our peripherals here, and then we can just write our high-level software calling the APIs generated from that.
and I think Josh was sitting mostly your MPLab X and MCC. I'm the unwashed child of the family here because I'm using Arduino, and the reason I used Arduino not to emphasize the rapid prototyping, but to stay that the as mentioned, that MPLab X sketch import is going to help a lot of people as they prototype an Arduino, which is a completely legitimate platform. I can prevent them from starting over again, and because a lot of their Arduino code is very well vetted, and it's been run millions of times, and I know there's some doubts on the reliability of the code, but in essence, with the sketch import now into MPLAB-X, you can go in and easily see if there's code that makes you uncomfortable, you can easily change it.
All right, thank you. Thank you very much. No more questions?
All right, well, thank you, Nate. And just a reminder that Design Week does not end with the live stream. We have a lot of content for you guys throughout the day. So if you go to Design Week 2023, click register, it'll take you to the On24 platform where you could check out all of the webinars available. Bob is doing the one about rapid LTE-M-based IoT edge development. And then we have Josh, who's leading the one on Learn the Smart Way to use on-chip hardware accessories to replace discrete components.
I have the bare metal one.
Oh, yes. And if you would like to go back to the one up here, it's getting started with bare metal programming using 8-bit AVR MCUs, and that one's led by Ross. So thank you very much, panel, for being here.
Thank you for having
Thanks,
me.
Ulysses.
Yeah.
Thanks,
Yes,
Ulysses.
thank you.
And I'd like to thank the viewers also. And I hope you enjoyed all 3 days of Design Week, and we'll see you next time.